Well, my dear, would you believe that Brigette Bardot is going to help us with a little problem in statistical mechanics? And here's the backstory. Half a year ago, I was putting together a little example on the one-dimensional cluster variation method, which is a method out of statistical mechanics. It involves a fancier, more complicated free energy equation. That is, the entropy term is more complicated than usual. And so I had this example, and the example was a one-dimensional illustration with a zigzag chain, a single zigzag chain, and it involved a text string. And I was assigning the consonants to be, they may have been off and the vowels on, or vice versa. I truly forget which was the case back in that example. So assigning them according to a simple little sentence, which was, please like me on Facebook, thank you. Which, no, let's not go there. Let's not go to Facebook. We're not doing that. I needed a really simple sentence. First of all, I needed a sentence that had equal numbers of vowels and consonants. And that gets rid of a whole lot of words in English language like night, K-N-I-G-H-T. I mean, the Anglo-Saxon derivation of words in the English language tends to have a lot of consonants. So I was going for those middle-of-the-road equal numbers of vowel consonants words and trying to come up with some silly little sentence that would just do as an example. And that one worked. And we got an example, and I think it got encoded into something someplace. I'm sure I've linked to it. Okay, we did that. And then over Christmas this last year, 2023, I put together another really simple little one-dimensional cluster variation method. Let's just call that 1D CVM for short. 1D CVM worked example. Just a toy, tabletop toy. And the reason that we're dealing with a 1D CVM is that the equation is a little bit simpler and the code is a little bit simpler. And it's our training wheels. It's our starter set. It's something easy to get into. So I did that. Launched it the day after Christmas, thought it would be a Christmas present for everybody, but hey, people were still having Christmas parties, so it didn't get too much attention back then. But now it's time for the follow-on. And here's the thing, we've had that 3-month gap, actually more like 4 months, and in that time I've put out a whole lot of stuff on generative AI, and really that foundational material for the generative AI is statistical mechanics. There's a wealth of stuff to draw upon if you need to do a little stat mech refresher. So the reason that we want this particular thing, the 1D CVM, is that we really want the 2D CVM, and we want that because it could be, we've got evening winds here in the island of Kauai in Hawaii. This is all real, you know, and the winds are real and they're picking up. So here's the thing. We want the two-dimensional version because it's going to be more easy to see clusters and connections between clusters. And as I mentioned before, you may have caught this, we want a connection between the single level representation. That could be anything that's coming into the system. It could be a large language model for all of you now. We really don't care. And then we want the symbolic level, and we want to connect the two, which is an essential step in creating an AGI. And to do that essential connection step, we're doing what the LLMs were designed to do, which was temporal association over really long periods of time. Actually, in an LLM, it's variable periods of time. You know, they have the varying degrees of sinusoidal positioning and positional encoding, along with their multi-head attention. So here we are. We want to capture important phrases that occur at various points in time and reinforce their presence so that they persistently maintain an activation up to the symbolic level. And actually at the symbolic level, we are going to have an activation ontology as well as the actual symbolic ontology. Big, huge, important topic of conversation. So subtle, so really interesting, but we'll go there a different day. Today, we're at that connection mechanism, which involves a CVM, cluster variation method, statistical mechanics capability, which is embedded in what I call a CORTECON, content retentive temporally connected neural network. But that's basically the wrapper for the entire system, where the CVM is the working engine. And to get this CVM working engine, we're going to try this time a slightly more complicated text string. It's actually 188 characters long, not just the few that were part of the original example. 188, 94 consonants, 94 vowels, because we want to have, this is the important thing, early in this game, while we're still teaching ourselves this, we want to have equal numbers of vowels and consonants, because that lets us access an analytic solution. And an analytic solution lets us contrast and compare whatever we're getting with computational results with what we get analytically. And it's like, are we close? Are we off? Does the whole analytic solution diverge at some place? Which it does, but we want to stay in a middle ground where it doesn't diverge. And we just want to get sort of a guy wire. It's like holding on to the ropes while we're learning to swim. It's a short-term safety measure. So here we go. The song sung by Brigette Bardot and her lover. I think she made him make this song for her. She wanted him to make the most romantic song in the world because they'd had a spat, and she was insisting that he offer appropriate recompense, shall we say. And I so totally believe, yes, lovers should be forced to offer a little token of tribute every now and then. It just keeps things spicy and interesting, So here we go. He writes a song for her, and she sings it with him, and there's a lot of moaning on her way to ecstasy. And because of that, Holy Roman Catholic Church raised a fuss. I think it was the French government that banned the song for a while. I think it got played extensively in England. And it quietly drifted off the airwaves, and then it was reprised later by no other than Jane Birkin singing the same words with similar moans. And I believe that both versions are available on YouTube. I linked to at least one. I think it's the Brigette Bardot original. And I don't know if I'm linking to any of the spicy stories. I may have to go and find them. Blog post, darlings. I'll link to a blog post. The blog post has all the details. Okay. In the French song, the words are je t'aime, je t'aime. I'm probably pronouncing it all right. It's like, I love you, I love you. Oh, I love you. And the man says, essentially, me, I'm not so certain. It's like sexual politics in a nutshell. Let's not go there. The words of the song give us equal numbers of consonants and vowels. And there was an English translation, courtesy of our good friends at Google. So I got the example put up with both versions, French and English. And this is so simple, so easy to use. You basically swipe the code out of the GitHub repository. I linked to the GitHub repository in the blog post, which is linked to in the description box below. We always do this. So you take the code, plug it into your Python idle, hit the run button. It is that easy. No directories, all the data is embedded, just to make it easy, And you watch it run. And then at the end, there's the configuration variable results. Those are like how many nearest neighbors of various types, how many next nearest neighbors, how many triplets of various types, then not the free energy. To do the free energy, you would have to run a pass with different kinds of enthalpy terms. And we haven't selected an enthalpy, so we're not worrying about it right now. But it gives us the entropy term. It gives us the entropy for the two different cases. Now, here's where things get interesting. This is why you want to do it, because this is where the fun is. The French and the English results, I wasn't too sure they would, but they did have slightly different positions on the analytic solution graph. I'll show it here. We'll do a voiceover, and I'll put it into the blog post. So for each of the configuration variable values, I've got to say that slowly so I don't trip over the words. Configuration variable values, and I'm picking just 3 to be illustrative. So one is the number of like, near, unlike. That would be on and off together, or off and on, nearest neighbor pairs. And then I pick 2 of the possible 6 different triplets. I think one is the AAA. It would be on, and the other is an ABA, or on, off, on triplet. And you put those 3 configuration variables together visually, graphically, and you get to see pretty much what's going on with the system. So 3 is plenty. And they don't necessarily line up because the system is not precisely, perfectly at equilibrium. And that's, of course, the first question that we'd ask ourselves when we apply this as a model to anything. is the system at equilibrium? If not, how far off? Because if these configuration variable values do not all sort of line up with each other, it means that some are like twerked in one direction and another one is twerked in another. The system is having a hard time getting to equilibrium. But in this case, they're kind of close, like forgivably within close, which brings up the second question, which is, different enthalpy parameters characterize each spot on the analytic solution graph, right? It's a continuous function, so smooth continuous function, analytic, and you can get a function of the, shall we say, the y2, which is the like near unlike, the a next to b, the b next to a, nearest neighbor, similar for all the others. You can get a function in terms of what I'm calling h, which is a function of the interaction enthalpy. Because we have equal numbers of on and off nodes, we are setting the activation enthalpy to be 0. That is, on is not more energized than off, equal numbers. So it's a game that we can play that reduces our situation down to a single parameter. Single parameter, easy to solve, easy to look at, easy to sense what's going on. So we've got this single parameter controlling the configuration variable values in the analytic solution. We are matching our observed against that. We get slightly different vertical lines against the enthalpy parameter h, which is a function of the interaction enthalpy, E sub 1, epsilon sub 1. And so we want to find, this is the next task, what would be the best, the most characteristic h value for each of these systems. And to do that, I've created a new divergence method, which we're not going into here. It's a subject for a follow-on vid. But let's just say that, as a matter of fact, we can find a model value. This is cool, right? We can find an interaction parameter value h, which is a control parameter that best describes that system for the given data that we've got. And so we wind up, once we've done the divergence method, which again, we're not doing it here, follow on vid, follow on little study, but we'll have two h values. So these two systems, the French and English, are not precisely on top of each other. They're slightly apart. We'll discuss that more later. So here we are, two data sets, two different positions of something close to equilibrium, two different enthalpy parameters, interaction enthalpy parameters controlling them. And what we can do with it is this. First of all, we've just modeled a system, so to speak, with this fancy little, not free energy equation, because we haven't really stepped our way through, but we could now. Once we use the divergence method to find the best h values for each of these two different data sets, we would then know the characteristic interaction enthalpy parameter that describes them at equilibrium, and that would be a free energy minimum solution. Yay, we've just modeled these systems with two different free energy solutions. That's really cool. Brand new toy. So here's where we could take this one step further. We're not going to do it here today. We're just going to leave it at the note of having the experiment that I'll show you shortly. You know, Carl Friston's work is all about active inference. And active inference is basically taking variational inference and saying, let's progress things forward in time, and we will try to advance the model so that when the system evolves, the model still gives us a free energy equilibrium in terms of comparing the model of the system against the actual observations. That is, you minimize the divergence. Coincidentally, you're minimizing surprise. So what we could do here is potentially model the evolution of a system through time, because we could construct a trajectory of the evolution of parameters of the free energy equation. And in this case, because we're keeping it so simple, we could keep that progression of parameters down to just how is the h value changing over time. We could even say, if I were to tweak one of those just a little bit, suppose that English were an evolving language, which it is, all languages are evolving. And we could say, suppose it was evolving in a certain direction, and we actually changed a few things in our data set. So not this time later system, I'll give you a chance to go in there and change a few of those on-off nodes, just swapping them around. We change the entropy of the system. That means that the H value characterizing this system, and that would bring it to a free energy minimum, would itself also be different, which would be an evolution in time. And we could play with this as a model evolution. And I'm so excited to get to that one in the future. For today, though, please enjoy this. This is a new play toy. It's going to be a lot of fun, so easy, and just whoever would have imagined that Brigette Bardot would bring us into the world of statistical mechanics. I'm Aliana Moren. I'm going to turn you over to a voiceover, but I'll see you at the end. Before we go into our tech details, let me just share with you where you can find the resources so that you can replicate all of this work yourself. First of all, we link to the blog post associated with this YouTube in the description box below. In that blog post, you'll also find a link to the blog post for the prior related YouTube, where we used a simpler example. That was back in September of 2023. In the blog post, you also find a link to our GitHub repository for this specific project. It contains a PowerPoint deck of all the data and the results that we are presenting here. And we also, of course, have the code. The data that we're using for this little mini experiment, this little tabletop experiment, is included within the code itself. All that you need to do is pull that code out of the GitHub repository, plop it into your favorite Python idle, and hit the run button. In creating the data set for this project, we were constrained by the need to have an equal number of consonants and vowels. Recall that we're doing this in order to access the comparison to the analytic solution. So because of that, we had to selectively cull a few of those verses in the French original lyrics, and then correspondingly similar ones in the English, and we added a single word, the word between, to the English language data set. We needed a few extra letters to bring our total up to the same number as we had in the French set. Also, the word was already in the data set, so it wasn't bringing in something extraneous, and it had the right number of consonants and vowels. So the program gives us our results for both the French and English versions. Let's first take a look at the configuration variable values. We have the values printed out for the various y's, those are nearest neighbors, the next nearest neighbors, which are the W's, and then 6 different kinds of Z's. And as I mentioned earlier, we can pretty much understand what's going on just by looking at 3 of these. The Y2s, that's nearest neighbor, like, near, unlike, and then the Z1s, 3 of the same together in a triplet, and then the Z3, which is an on, off, on triplet. In the program, we give the values for 2 times Y2. We use the same mechanism to count the on, near, off, as we do the off, near, on, nearest neighbors. And just note also that the way that the CVM code and the whole mechanism is set up, nearest neighbors are those on the immediate diagonals. The 2 nearest neighbors for a given node would be the nodes in the row immediately above it or below. In this case, we only have one of those options available, since we've just got a one-dimensional zigzag grid. Now we're about to go into a bit of technical detail at a level that I haven't broached before, and the best resource for having a really detailed conversation on these topics is the 2016 paper that I published in Brain Sciences, and of course the link is in the blog post, and you can get the link to the blog post in the description box below. So let's have a little look at this analytic graph that I've referred to so often and get a sense for what to expect as we change the nature of the data. First, you'll notice that vertical line, it's centered at h equals 1 or epsilon equals 0, and h is a function of the interaction enthalpy parameter, epsilon 1, simplified here to simply epsilon. In fact, h is the exponent of epsilon over 4. So when epsilon, or the interaction enthalpy parameter, is set to 0. That is, there's no preference for a node to interact with a node like itself or of the opposite type. So you're going to get a strictly random chance distribution. So for example, for the y's, or the nearest neighbors, you're going to have an equal number of, let's call these nodes being in state A or state B. You'll have an equal number of A next to A next to B next to A, and B next to B. And that's assuming that we're counting these Y2s, the A next to B and B next to A, starting, for example, from the left and moving to the right. Let's identify the Y2 graph in this figure so that we have something tangible for our conversation. It's the one in the short dashed purple line, and it starts at the upper left near about 0.5, drops down to 0.25 when h equals 1, or the interaction enthalpy parameter epsilon 1 is 0, and then it continues to decrease. Let's refer very briefly to our free energy equation. We see in this equation for the 1D CVM, the term epsilon, this is our epsilon 1 because epsilon 0 has been set to 0, and it's multiplying a linear combination of triplets or z values. We can express the y values in terms of combinations of those z's, so really what we're looking at is epsilon times various combinations of the y values. When we have y2, which is a sum of certain of these z values being multiplied by epsilon, and epsilon is a positive number, we wind up adding energy into the system. But the whole idea of free energy minimization is that we want to minimize or lower the free energy. Thus, when epsilon is greater than 0, we want to have y2 as small as possible. Similarly, if epsilon is a negative value, meaning that we lower the free energy of the system by having an A near B node or a B near A, then we want to increase the total number of y2 values or A near B, B near A pairings. With this in mind, let's take a look at our actual results. Here's the output when we run this little snippet from the French language into the system, and we see that 2 times y2 is 0.638, or y2 is about 0.37, and isn't that interesting? That is significantly more than the random chance value of 0.25 for an A near B or a B near A. What that tells us is that we're getting like near unlike, that is, A near B or B near A. In our case, that means consonant near vowel or vowel near consonant, more often than by random chance. And of course, when we take a look at our text string, yes, of course, I love you. That's vowel, consonant, vowel, consonant. So you'll see that repeated more often than chance throughout the entire text string. So let's put all of our results together in one graph. This is for the French language, and we see that the vertical lines here, green vertical line for Z1, that's the vowel, vowel, vowel combination. Recall that we're making our vowels to be the on nodes for the particular way that we're encoding things. We've got values for Z1 that are far to the left. We have a smaller number of vowel, vowel, vowel combinations than we would expect as compared to random chance. Similarly, the values for Z3 and Y2 are greater than random chance. That means that we have more Z3, that would be vowel, consonant, vowel. And yes, that's kind of typical from our little song snippet. And then also Y2, we just discussed that. We've got more vowel near consonant and consonant vowel pairings than by random chance. So, okay, these aren't exactly totally lined up with each other, but they're in the neighborhood, good enough. We're not going to try to do that divergence method and get an exact H value to try to model the entire snippet. That would be a different video, a different moment in our time. But let's just say that the H value is sort of in the neighborhood of 0.7. So let's wrap this up by looking at similar results as applied to the little corresponding text snippet from the English language translation of that French song. And we see right away, the 2 times y2 is significantly higher than it was in the French version. We've got 0.734, so half of that for a given y2 is about would be about 0.38, and that's more than the previous value that we had for the French value. And similarly, the z1 looks a little bit lower, the z3 looks a little bit higher. What that tells us is that in this particular English translation of that French song, just those few short little lyrical phrases, we have an even more pronounced tendency to have consonant-vowel, vowel-consonant pairings. And we might ask ourselves, is this typical of English? And let's just imagine a phrase. We're going to create an Anglo-Saxon-based phrase in English, something like, the knave took fright at the sight of the knight. And we've got all these beautiful KN, knight, words and GHT words, so typical of English and some of the other Germanic tongues. So, wow. No, this is not typical at all. It's strictly an artifact. We're not proving anything about the English language clustering of consonants and vowels versus the French. All we're doing is showing how this method works on strings of data. We're just putting a little tabletop example into play so we can compare results. But let's go ahead and compare those results. So let's take a look at our French language results once again, and we see that that H value is sort of in the neighborhood of 0.7. We wouldn't know the exact until we ran a divergence measure. And then let's take a look at the English language values. I'm superimposing a graph around where the French values were in the English language version. So the French values are in that smaller, pale, dashed pink box to the right of the larger pale pink dashed box, somewhat to the left and overlapping. The English language version has an H value of about 0.6 if we were able to converge via divergence onto a single value that described all three of those configuration variable values, and of course all the ones that we haven't looked at today. So, okay, what this tells us about the English and French languages in terms of their preference for vowel-consonant combinations is, frankly, nothing, because we already know that English would lead a little bit more towards the center. It's got a very consonant, near consonant kind of vocabulary. But that would be more of an analysis than we're after. All we wanted to do was have a new toy, to play with a toy, to investigate the possibility for saying, oh wow, if there's a way that I can come up with a single zigzag chain that describes on-off units, it's got to be bistate, then we could characterize the clustering, and that's something fun. And then we can envision if we can go into a two-dimensional version and really see some clustering behaviors. Wouldn't that be interesting? So today is truly just a prelude. We could have an extended conversation about how this method, as it fits into CORTECONs, fits into variational inference, active inference, connecting between signal and symbolic layers in an artificial general intelligence system. But that's too much jumping back to a high level. Today we've been very granular. So the fun thing to do right now is to go get that program, run it, and play. And there are a lot of other YouTubes leading up to this moment. Full-scale code walkthrough of the earliest version, another worked example, lots of details supporting this if you'd like to play with this new toy. Once again, this is Aliana Moren from Themesis. Hope you've had a lovely day. We've so enjoyed this moment with you. We'll see you again soon.